with the Maxwell's equations came to your mind, can come to your mind as convincingly rather than just like magic, I wrote down two equations.
What's the J on the right-hand side of the second matrix?
Current density. I want to finish this one before I talk.
What's D? Okay. Okay. In here are four equations. Two equations with curl and two equations with divergence. And mathematically speaking, E, H, D, and B, and rho, and J, and so on, these are all vector functions of x, y, z. And I wrote them in the form of e to j omega t. We don't have to do that. We can just make this a d by dt on that, d by dt on that. Then we're talking about the real fields. So let me do it this way. It makes no difference anyhow in terms of the mathematics of it. Now, here, del cross E and del cross H, delta D, delta B. I'm sure you have been exposed to the form before. Say delta D will be something like a d by dx, dx plus d by dy, dy plus d by dz, dz, and all that. And B is like that. Curl will be some kind of a determinant, and all that. So that's the operational form. Operational form means that is when you want to calculate the curl or the divergence of a certain vector function of x, y, z, you plug into those formulas. And the different coordinate systems have different formulas. In XYZ, I just said it, in other coordinates, cylindrical, spherical, you have different forms. They're all in the books. Okay. But the important thing is to understand that intuitively what it means. So if you say, what is the d by first derivative? What is df dx if f is equal to x cubed? Okay, d by dx on x cubed. You say it's 3 times x squared. Right? Now this is one thing to understand that. It's just to say these formulas there, all the differentiation formulas there. Those are formulas for you to work with. Okay, the real definition of a derivative is not by those formulas. The real definition or the concept of a derivative is a limiting process. Okay, so I'm sure this you know. If this is f of x, let f of t. Okay, let's say this is t. Then what do you do? You say this is f of t. First of all, what is f prime of t? Okay, f prime of t is also a function of t. How do we get that? I'm using this to lead you to understand all that. Okay.
So rate of change.
Yeah. We said f prime of t is this. You take this, you take this. So this is called the delta t. This is f of t plus delta t minus f of t divided by delta t. Limit delta t go to 0. This is equal to f prime of t. Okay, so this is a mathematical definition. What it means by f prime of t. Okay, it's this limiting process. Take the value at this point, take the value at that point, take the difference, that's that. That's the numerator. The denominator is delta t, is that. So that over that is the slope of the secant. And when this limit goes to 0, delta t goes to 0, this point approaches this point, now you have 1 point. Here, that quantity is the slope of the tangent. Okay. So if this is distance, f prime of t will be velocity. If this is the velocity, the f prime of t will be acceleration and all that. So you tie a rigorous mathematical definition with a mathematical intuition, with a physics intuition, implication. All right? So this you have done it many times before. LDI dt and so on, it's the same thing. Now we're going to do with this.
Okay. I intuitively was thinking a lot about this, and it makes a lot of sense because the derivative of E field, the tangential vector component.
Okay, let's not get that far yet. This is something which is very profound. Even after when I teach graduate EMT, with PhD students, many of them would have to have this being imposed to them. For undergraduate EMT, this will take several weeks to get the whole thing straight. Very rigorously stated. So let's do this one first. Delta t equal to rho. Okay. First of all, I define in this fashion what means by delta d. Okay. Delta d is equal to all right. Now we looked at that. We define by this fashion f prime of t at this point. At a certain point of time, f prime of t is this way. So this time can change along here for different times, then you do it similarly. Now what this means, this says the following. First, mathematics. D is a vector function of xyz. For the moment, I don't care what physical quantity that means. Just a mathematical function of xyz. So therefore, it fills the space. Every point in space, there is a value of d, has three components, dx, dy, dz. And each is a function of x, y, z. Okay. So that's a vector function of x, y, z. So I first to do is at this point here, I take a little volume.
Surface.
Okay, little volume, and this volume here has a surface delta S. Okay. Now, so this is a little sphere in here. Now, on this surface, there's D everywhere. Okay.
With direction.
With direction and all that. So N is the outward normal.
Radially?
No, normal to the perpendicular to the surface.
Okay.
Okay. The surface, if it is sphere, then it's radial.
Okay. Let me ask you a question. The delta V, is that some volume measure?
That's the volume.
Okay.
Delta volume is the volume of this little volume. Delta S is its boundary.
Okay.
Okay. So now
It's a
we are.
surface integral. In three
Okay,
dimensions.
now what we do is we take the surface integral. D dot N actually means the number of the flux lines coming out of the little surface ds.
Okay.
ds is this little surface here.
So we're integrating the total number of D lines coming out of a surface that's eventually going to zero.
Okay, now that's the number of flux lines coming out of that. Then, so I do that, I get a number. Then I have that number divided by the volume of this thing here. Then I make the volume smaller, smaller, smaller. The numerator and the denominator has a ratio. Both of them go to zero, but the ratio,
Infinite
It-
series. Not infinite.
limiting
series.
process.
Limiting process.
Okay, that process will make the ratio the same. Just like the ratio of this to that, it's 0/0, but the ratio is a good number, it's a finite number. So this is the definition of divergence. Okay, so so this is a divergence is some kind of a derivative operating on a vector function of x, y, z. All right, it's given by this. So this is amounts to this, more or less. If you think about, you take delta V being 1 unit by 1 unit by 1 unit by 1 unit. If this is your delta V, all right, okay. So d dot nds is d comes out this way, and d comes out that way, or plus or minus d comes in that way, right? Then delta s will be this area times delta x here, all right. And you make delta x go to 0, it's like a delta v go to 0. So this is exactly that. All right, this is exactly that. All right. So this is like a f of t, f of t plus delta, f of x plus delta x. That is f of x, okay. Coming out becomes minus. So the sum of these two will be essentially that. And then divided by delta x times 1 times 1, that makes it, so it's, of course, in this case here, you have to take flux coming out of here, flux coming out there, and so on, right? So it's a three-dimensional. But nevertheless, you can see the analogy between the two.
Okay. The physics of the rho.
Now, okay, let's look at what the physics means. Gauss's law. Gauss's law says that if field have charges.
Yeah.
Okay, you take a surface.
Right. What's Q again?
Q is charge.
Okay.
Okay.
Total number of Q.
Total number.
Okay.
Total. You take. So this D actually is equal to epsilon times E, right? Okay. So the number of flux lines coming out of a closed surface equal to charge enclosed. That I think you remember that. That's the Gauss's law. Okay, so now we look at that. So which means if instead of a big sphere, I have this Q is 5 coulombs here, minus 2 coulombs there, 3 coulombs there, minus 1 coulomb here, and the total sum inside this sphere. That's that Q. So now if I take, instead of this big S, I take a small s here.
Okay.
All right. So change this delta S. All right. Then this Q will be the Q inside there.
Yes.
Okay, so that's delta Q. All right. So I divide by delta volume, delta V, divide by delta V.
That's the change in Q over the change in volume.
Not the change in Q. Delta Q is the Q inside that little volume.
Okay.
Delta Q over delta V, take the limit of delta V go to 0, is called rho, is charge density.
Okay.
Now, so you think about a cloud. There's some place the cloud is dense, some place the cloud is rare, is less dense. Then you take a volume there, and you want to see what it means by the density is high. It means it's crowded.
Yeah, I understand
Okay,
that.
so that's that. So therefore, first time you now have one Maxwell's equation. That's this Maxwell's equation coming from Gauss's law. Gauss's law is sort of an experimental observed effect. That is, it works in that. Okay. So once you have that, then you immediately get this one. Because what is B? The magnetic field lines. Magnetic field lines has no such thing as magnetic charge. So magnetic field lines always terminate on itself. You take a coil, the field lines go through it. All right? So magnetic field lines always terminate on itself, which means you take a sphere, any sphere, the number of lines coming out equal to the number of lines going in.
Always.
Always. Okay. So you coming out, going in. Inside here, you may have one loop like this. Once it goes out, it must come in. Okay. So therefore, there is no such thing as magnetic charge, or the net number of charge lines going out equal to the number of lines coming in. So the surface integral of this B dot NDS is always equal to 0. The total net number of lines going out of a closed surface must be equal to 0. As many lines going out as coming in, therefore, the net is 0.
No, I understand.
Okay, so therefore you can say mathematically so that goes to 0, or physically you see there is no such thing as magnetic charge, so therefore this is equal to 0. So you have two Maxwell equations. So now we see what we have done. We have acquired extending our knowledge from freshman calculus, but the very rudimentary definition of a derivative. Then we see this quantity here has some meaning of derivative in the sense of limiting process, infinitesimal divided by infinitesimal and all that. So now, do one more thing. I'm taking a volume. Delta V is Okay, this is XYZ. This is X. I'm sorry, that's not XYZ. That's XYZ. P of XYZ. Okay. So this is delta X, this is delta Y, this is delta Z. Okay. A little cubicle. The three sides are delta X, delta Y, delta Z. So this point here is XYZ. So this point is what? This point is X plus delta X, Y, Z.
Which point?
This point.
Oh, okay, you're coming out of the board.
I'm coming out.
Okay, okay, okay.
Okay. So this point here will be X plus delta X, Y plus delta Y, Z plus delta Z.
Right, okay.
Okay. So you know all these 8 corners now.
Yeah.
Okay. So that point is XYZ.
XYZ, yeah.
Okay. So now let's see. I want to do this. D dot N ds equal to, I have to do it on 6 sides. The total surface, there are 6 sides. Okay. The back, the front, the left, and the right, the top, and the bottom.
Right.
Okay. So it's a back, front, plus left, plus right, plus top, plus bottom. Okay. So let's do the top, back, and the front first. So now, so I have to do this. D back in the back there, D equal to, okay, D. At what point? Okay, let me, okay. So let's see, back is a point here. And this is X plus delta X. I'm sorry, X, this is Y, XYZ. This is X, Y plus delta Y, Z, and so on. So right now, on this surface here, D, we are on X equal to X, okay. Y go from here to here, Z goes from here to here. You follow?
Where?
Okay, so we want to do the back, right?
Okay,
Back means that direction, right?
okay.
We want to know how many flux lines going out of that back face.
Okay.
All right. So therefore, what do? We take this as a flux density, integrate it over that back side.
Okay.
All right. So so what is a typical point here on that surface now? Okay, this is the surface. A typical point here.
Yeah.
Eta. Okay. Instead of eta, got it. Y prime, Z prime. So this point here, because it's in the back face, so it is X.
Defined.
Okay, it is there. Then Y prime is the variable of integration. You will integrate it from here to here to here to here.
Right.
Okay, so Y prime Z prime. So D. So what is N?
Normal vector.
Normal vector. So now N is the outward normal.
Right.
So which makes it minus AX.
Okay. Because it's outward.
Because it's outward. Okay. And then what is ds? ds is dy prime dz prime.
Okay.
Right?
Okay.
Then in the back that the integration goes from y to y plus delta y z plus delta z, right?
Right.
So d dot minus ax becomes minus this integral dx, the x component of that. But it's minus sign in front here. Okay, x, y prime, z prime, dy prime, dz prime, right? And goes from
Same thing. Y to y.
yes.
delta y.
Okay, so I don't want to do that then. You know what?
Just
I don't
go.
want to write it. Okay. So now eventually I'm going to take delta y to go to 0, delta z to go to 0, right?
Mhm.
So maybe let me be fancy. All right. Okay, I don't want to be fancy. Okay. This is the y integration, y prime integration. If this doesn't change between here and here, all right, this just simply becomes dx x y z times delta y delta z. Right. So since this is going to shrink to 0, over that delta y delta z, this doesn't change.
Okay.
Okay, so this is back. Front. Now I'm on this front here. All right. Again. Oops. Okay, in the front, okay.
Sorry.
In the front, this n is what?
In the front, it's positive.
Yeah, it's positive AX.
Positive AX, right.
Right, AX. So again, dy prime, dz prime. So this goes to become dx of x plus delta x, y, z, delta y, delta z.
This is an extension of this, the Maxwell equation, right? This is for that.
This is doing that. This is what I'm trying to do now, is to get to the formula you are familiar with. All right. So front plus back will be equal to dx of minus dx of x, y, z, delta y, delta z, plus dx of x plus delta x, y, z, right? Let's combine those two. This one and that one. Delta y, delta z. Okay. Then front plus back divided by delta v, limit delta v equal to 0 is equal to limit. Okay. Delta v is what? The volume of this thing here. It's delta x, delta y, delta z, right? So it's the dx of x plus delta x, y, z, minus dx of x, y, z, delta y, delta z, divided by delta x, delta y, delta z, right?
Right.
Okay. So delta yz cancel out.
Right.
What is this?
Limit, that's the same thing as a derivative.
That's now in this case here should be partial derivative because
Delta x, delta y.
only delta x. So this is equal to d by dx dx.
Oh, I see what's going to happen. This is going to be partial d by dx, d sub x dx plus d by plus partial d sub y plus blah blah blah, which is the definition of a dot product.
That's right. But it's not a dot product. It is the formula for
Solving a dot product.
the formula for divergence for delta d in xyz coordinate.
Right.
Okay. So therefore, finally you have delta d equal to d dx dx plus d dy dy plus d dz dz. Alright? So now, the definition of delta d is the one I had before, was the integration, limiting, and so on.
Right.
That's the real
That's the formula.
fundamental definition.
Right.
When we apply that definition to rectangular coordinate system,
We get that.
we get that. And you can do this with a spherical coordinate system, cylindrical coordinate system, or use this as a basis to do coordinate system transformation.
Yeah.
Okay. So therefore, let's just trust that they did it right. Okay. So therefore, it's no longer mystery. From Gauss's law we had before, through the definition of a divergence, we obtain this equation. Further, we know the left-hand side is that in rectangular coordinate system. By trusting the people who done it in the past, we also know the left-hand side could be something different in cylindrical or spherical coordinate systems. I don't remember them. Every time I need it, I look at it in the book. Okay. Probably it's like this. Okay. D by dx d rho, d by d rho d rho plus 1 over rho d rho.
And then 1
d,
over r
d by
squared.
d phi plus d dz dz.
That's cylindrical.
That's cylindrical.
There's a 1 over rho squared for spherical. Something like that.
That's right. It will be. Okay, so that's in the book. Okay. Now what I'm going to do is to do the curl. Doing the same thing for curl. Okay. The definition of curl is equal to, first of all, this is also some kind of differentiation operating on a vector function of xyz. Similar to that. However, there is a difference. This yields a scalar. This, however, yields
A vector.
a vector. So therefore, the curl of a vector function
Is a vector.
is a vector function of x, y, z. The divergence of a vector function is a scalar function of x, y, z. Okay. This rho is a cloud distribution. Different values at different places. A smoothly varying cloud. So let's see. So it is a vector function. So we have to define a certain direction because we say it is a vector, so a vector is defined by its three components. Hi,
Hello.
you're here.
Yes, I'm here.
Okay, I'm working with him now.
Okay.
You said 1 o'clock.
Yeah.
Suppose I come to look you up
Fine.
in 1 o'clock.
Fine.
Okay,
Very good.
okay. How did you get in?
You have a doorman here.
I see.
And I was standing at the door.
I see. Okay, del cross H. Del cross H is a vector function. So I'd say delta x function on a direction A. That means the A component. Okay, the A may be AX, AY, AZ, maybe AR, any particular direction I define. Okay, that's A. So what will be the definition of the curl? It's A components. Okay. So if you have any problems, I can do this. Change this to X. Okay. Now what I'm going to define is the X component of a curl. Curl of H. Okay. There could be Y component and Z components. Right? So X component is what? Is defined by the following. Okay. Now,
It's a line integral.
that's right.
It defines a ring.
Yeah, a loop.
Okay.
Okay, maybe I should use AX. Okay, so now what that means is I have, this is a vector function for H, okay? It is fill up the space everywhere. So I take a loop. Okay, it doesn't have to be a circle,
Okay.
okay? Now, I wanted to do it to find the curl's X component. Then this delta S in here, this surface in here, this is delta L. This is delta S. Okay, delta L is the boundary, delta S is the surface.
No, I got it.
Okay,
I know
got
what
it.
this is.
All right. So, so delta S is perpendicular to AX, so the AX must be coming out of the blackboard or going into the blackboard. Let's say coming out of the blackboard. Okay, X in this direction. This line integral follow right-hand school rule with AX. So I'm not doing this.
Yes, that's correct.
Okay. So which that means I take along here the value of H at this point dot dl in that direction times this dl. All right? Then take the next point, take the H at this point, find its component along that direction, and so on. Continue that adding up. Do you get it?
Well, if okay, let's start again. Okay.
Okay, start
Is
again.
okay. because I already see something. Okay,
Don't
but
jump,
I'm not,
don't jump.
I don't want to jump. I just
Right.
want to see whether I understand this
Yeah.
part. Okay. Well, unfortunately, that's part of it.
Yeah.
You know, I mean, I see
Yeah.
pieces together, and it's causing me to be confused. Okay, we're taking a line integral around a surface. Okay.
Not
and-
around the surface, along a line, a closed loop.
Okay, we're taking, well, in this particular, we're doing a closed loop.
Right.
Okay, and we're integrating along the length of the loop,
Right.
and we're going to get a directional vector at every delta L.
Right.
Okay, S is the direction of the vector. I don't understand what I don't know what you're doing with delta X. Okay, I really don't. Delta S.
Delta S, if this is delta S, is the surface.
Yes. Okay.
Delta L is its boundary.
Okay, that I got.
Okay, you got it. Now, I want to find, I first said that curl of an H is a vector function. Alright? Curl of H is a vector function. So
Okay.
therefore, the curl of H has three components. Understand? Okay, now look, okay. You have a magnet there, all right? Magnetic field lines fills this room. A powerful magnet there, the magnetic field lines fills this room.
Okay, go ahead. I see. The thing is that the second you draw a loop
Yeah.
in a magnetic field, when you know,
Now, let's forget about the magnetic field. I said just think of magnetic field as a vector function of x, y, z,
okay.
which means this is x, that's y, that's z.
Okay.
All right. I want to know the curl of H at this point.
All right, go ahead.
Okay.
I
Okay, just listen. Okay, I want to know the curl of H this point. I said I wanted to know all its three components.
that's the only way you can get that vector.
Okay, because the curl of H is a vector, so therefore I want to know all its three components. Now first I want to know its x component.
Okay, we're only doing X right now.
We're only doing x
Okay,
right now. Okay,
that's the part that's kind of bothering me.
right.
Okay.
We do the x now. Okay, the x component now. All right.
Okay.
So how am I going to find out the x component here? First thing I will take a delta s, which is a perpendicular to x. This is x, so this is, at this point here, I get my delta s here is my palm.
Okay.
Then I have a delta L is this circumference of my palm. All right?
All right. Go ahead. I mean, the reason I keep getting stuck is this cross product, vector cross product.
Don't worry about the crossing here. This, you don't need to even see del crossing here. You just say curl. You can call it curl.
Okay, go ahead.
Okay? Just, we're defining a new derivative.
All right.
Okay? Like the divergence we did it earlier. You didn't see the d by dx, d by dy, d by dz until the end.
Okay.
In that process, we're doing it, we didn't ever mention xyz even.
Okay, go ahead.
All right, so now, so I want to know its x component. This is x direction. So I say, over here, magnetic field lines fill this room, so I put this delta s here. All right, delta s here. Then this is delta L.
Okay.
Okay. So I said, now I'm going to perform a line integral.
Okay.
In what direction then? Right-hand school rule says in this direction.
Okay.
Okay. Now you look at that in this direction. All right. So that's that in that direction. Now, along here, at each point here, I see how much is h here, in what direction it is.
Yeah.
So maybe something like that. maybe something like that.
Uh-huh.
Okay, you take the dot product of that along the tangent dl,
Okay.
okay, times a little distance dl, okay, then move to the next dl.
No, I understand the mechanics of what you're doing.
Okay, so that you do it first. Once you go the complete circle, loop, close the loop, you get this line integral.
Okay.
You get a certain value now. You get a number, right? You get a number. These corresponding to this summation of these guys in here. You divide that number by the area of my palm.
Okay.
All right. So you get a ratio of these two numbers.
Right.
Okay. Now then you make a smaller loop.
Uh-huh.
You repeat it the same way.
Okay.
You can take the ratio.
Mhm.
You take a smaller loop, you take a ratio, you take a smaller loop, you take a ratio. As these loops getting smaller and smaller, this integral and this delta s both getting smaller and smaller. But the ratio of the two approaching a constant. Okay, the ratio of the two become a constant. So that number, the limit value of these two ratios, is equal to the x component of the curl of h at that point. At this point when the loop shrinks to 0. Alright. So that's curl. Alright. So now by the same token you can find its y component and z component. You can find it that component or that component and that component. All you have to do is put the delta s perpendicular to that direction. Okay. So you can take this delta s in all directions, you do this process, you can finally find a certain direction that's maximum.
Mhm.
Then your curl of h is in that direction.
Okay.
All right. Now this is algebra mathematics. I will just go to the next step here, and I have to go to see Jerry. Then I come back and give you some chance to transcribe the notes. What is Ampere's law? Ampere's law is this. Which means
Yeah.
okay. So this is the magnetic field lines H. So H dot dl integration along here equal to the current enclosed.
Right.
All right. So if I make it the delta L, means instead of a big loop in here, I have a small loop in here. All right, small loop in here. So what will be the result of this line integral then? The result of that line integral is equal to delta I. What is delta I? Delta I is not the whole current, it's only this current inside that loop. Okay. Divided by both sides by delta S. Now what do you see? That J. So limit delta S go to 0. So this is equal to J. Okay? Now, if we did this in the x direction, this will be Ix, this delta S will be perpendicular to x, this will be Jx. So we repeat y component and z component, add the three together. You get this, J, curl of H equal to J.
What happened to the j omega?
That's right, okay. This, however, you remember, this is only good for DC,
Oh, it's the AC current.
okay? So this,
That would be omega 0.
this is DC, right?
Okay.
Now, I don't have time now, I'll come back to do that with you. This part is called displacement current. All right. Displacement current is something like this. Suppose that we have a capacitor here,
AC current.
Not necessarily. A current flowing this way. If this current is increasing, all right, that current equal to that current, right? If I have current goes into it, which means I have positive charges goes on to that.
That's first order differential equation.
No, no, no.
The current
Okay.
is.
I don't know how the current, what current is equal to. I know that this moment here, I have I amperes going in here.
Right.
Okay. Which means the surface here, charge will be increasing because I have, each second I have I coulombs dumped on this plate.
I understand how displacement
Okay.
current works.
Which makes this side here negative. Which also means this current here taken out I coulombs per second out. So therefore, the negative charges here increasing. So you have plus charge, you have negative charge here. You have electric field in here. Okay. So this current here is continued through this electric field going out. If DC cannot go through a capacitor, so the DC current has to be 0.
Yeah.
Okay. If it's AC, that means this goes this way and that way, this way and that way. The current goes in and out, in and out. So you have in here there's electric field in here. So this total flux in here going through here is equal to total displacement current. All right. So I come back with you. So this is the most important contribution of Maxwell. Before Maxwell, Faraday only knew about this part here. He didn't see this part. This will create some ambiguity because there's something called ambiguity called this continuity. The charge is not conserved and things like that. So he saw this part coming in. And the important thing then, therefore, this comes from the Faraday induction law. Okay, the Faraday induction law. This is actually a voltage equal to dV dt. That's this equation. So this is Ampere's law plus displacement current concept. These two equations created the wave equation. From that, electromagnetic wave comes about. Before that, this particular point, before the displacement current concept got figured into the differential equation, all we had was just some rudimentary experiments. Rub something on the
Yeah, he defined the world in AC.
Picard or the compass turning this way and that way, and some
He
rudimentary
created the world of
experiment.
AC.
Right. It's more than AC. It is It is an electromagnetic wave.
Yeah.
Okay, comes out of it. Now what I want to do is to see how can I translate this definition into d by dx, d by dy, d by dz, that sort of thing. Just like what we did for the divergence. Okay. So what do you do? Here is a point here. So it has coordinates. It's x, y, z. All right. So I want to do is to find the x component. So x component, which means I have to take the delta s perpendicular to x direction. So this is the loop I want to take. Okay, that's the loop. Then
Perpendicular to the x direction.
yeah, this is the
Okay, I got it. All right.
in the YZ plane.
All right.
Okay. It's perpendicular to x, so it's parallel to YZ plane.
Okay, got it.
So now I want to determine a direction of integration. So it, with respect to x, it follows right-hand rule. So-
Counterclockwise.
Right. This is the direction. So this h dot dl equal to left plus right plus top plus bottom. So left plus right. Okay, left is this one, right is that one. So this is x, y, z. This is x, y plus delta y and z. This x, y plus delta y, z plus delta z. This is x, y, z plus delta z. Right?
All right.
So left will be from this point to this point. Right. So this is z prime. That's h dot dl is equal to hx dx hx evaluated, okay, any particular point here is z prime. Is hx y z prime dz prime integration from, this is left. All right. Integration is from z plus delta z to z. Do you see what I'm doing?
You're integrating along a line.
Along this line here.
Right.
Okay, that's left. Right is this one here. H x
plus delta x.
that's still x y plus delta y
Oh, z.
z prime.
Yeah.
That's z prime here. dz prime. Now it is from z to z plus delta z. This is right. So left plus right divided by delta s. Delta s is equal to delta y delta z. This is equal to, this is equal to minus, because the delta z is downstairs. Right? So you can flip the integral, put a minus sign in the front. So minus hx x, y, z, delta z, plus h x x y plus delta y z delta z divided by delta y delta z. So delta z goes out of business. So this is equal to limit delta y equals 0, delta z equals to 0. And this is equal to partial hx, partial y. You see it?
Hold on, I'm not done. That's h of x. This is cancelled. Okay, yeah. All right.
Okay. So so left, this is left plus right, top plus bottom. So top, bottom is this one. Okay, bottom h dot dl equal to integration from variable of integration is y prime hy I'm sorry, this is no wonder. This is wrong. This should be hz. So I wonder what's going on here. This is z direction,
Right.
right? So hy, this is hy.
So the ones above it are also h of hz.
This is, that's right, hz. Hy of x, y prime, z. dy prime from y to y plus delta y. Okay. That bottom, the top, h dot dl is equal to hy x y prime z plus delta z dy prime from y plus delta y to y.
Okay, that's the top part.
That's the top part. So therefore,
Top plus bottom.
top plus bottom equal to
Where'd you go?
hy x y z delta y minus hy x y z plus delta z.
Over.
That's right. Times delta y
Over.
over delta y delta z. Alright. So delta y cancel out. So this
Partial
is
y
this is equal partial
One.
hy
over partial z.
partial z. Something is wrong. I missed the minus sign somewhere. Oh no, this is equal to minus that. Right? Positive that is this minus this
Right.
divided by delta z.
Right.
So it's this minus that.
Oh, okay, yeah, the delta
Okay,
y.
delta
yeah.
z is here. So that's minus here.
So the addition is the
So therefore, del cross h, the x component is equal to
partial.
dhy dz minus dhz dy.
You got it backwards.
I've got it backwards. Okay.
Then you have the same thing with hy.
So now this is the x component. Now I want to find the y component. I have to take a loop like that,
Right.
perpendicular to y.
Right.
I want to find z component, take loop like this.
Right.
Okay, just repeat the same process. So as a result, del cross h is equal to this determinant, ax, ay, az, d by dx, d by dy,
d by dz.
d by dz, and hx, hy,
y, hz.
hz. So you just check the
I remember
x
how to-
component
Yeah.
is this way, dhz dy
Yeah.
minus dhy dz.
Right.
I think we got it right. dhz dy minus dhy dz.
Right.
So the x component, the y component will be dhx dz minus dhz dx. That's
Right.
y component.
Mhm.
Z component will be dhy dx minus dhx dy. So so now we see the left hand side here, these two guys here, both are
Determinants.
derivatives contains the d by dx, d by dy, d by dz, all right, of the components. Okay. In this case here, it has three. This actually has three equations. This has three equations. All right. Now, important thing is to get a little bit more physics into it. This is so-called displacement current. Actually, this is in the frequency domain, so-called e to j omega t.
Right.
In the real field, is a del cross h is equal to equal to d by dd dt plus j.
Okay.
Okay.
But I thought D and E just differ by a constant.
That's right. Differ by constant. So it's not differ by time. I put the D in here. This is getting a little bit complicated, but I don't want to mislead you. It could be just epsilon 0 dE dt. That's fine. If you have a material that may not be so good. But anyway, let me put it this way. That's too sophisticated. Let's not for this cram course here. Normally I couldn't even do that in my graduate course. What's the factor is, what's the epsilon? Epsilon, what makes epsilon different from epsilon 0 is because the molecular charges, electrons and
Yeah,
so
it's the permittivity
permittivity.
constant. That's basically what defines how well an electromagnetic wave will propagate through a medium.
Not electron, how an electric field, you put inside the electric field, put this piece of material inside electric field. How the molecules in there,
Will
the
line-
charges will realign itself.
realign itself.
Okay, so it's not a wave propagating through. You have to not to use these terms arbitrarily. Electromagnetic wave propagating through, of course, the epsilon affects that.
Great deal.
Yeah, it's a function of that. But for the fundamental definition of epsilon is when you have, it's immaterial whether you have a wave or not. You just have a piece of a dielectric. You put inside an electrical field.
And then what happens?
Then what happens to the electric field lines? It's a DC, could be. So basically, is what happened is that the field, take a simple molecule or atom. You have a nucleus in the middle, electrons drawing circles
How it
around it.
turns and everything.
Drawing circles around it. Once you put the electric field between the orbit, elongates a little bit. As a result, you have an induced dipole. In other words,
No, I understand.
you understand? Okay, so anyway, let me redo that. So get to this one here. Now, if you think about something else, let's think about this. If I have a closed surface, okay, I'm blowing electron wind through it. I'm blowing electron wind through it. And there may be mountains here, traps here, and I don't know. But anyway, blowing electron wind through it. Then
Does that signify current?
that's of course a significant
Okay.
current. Okay.
Just making-
So I have a current goes in and goes out, and some charges stays, some electrons stays a bit longer, or sometimes more electrons get spilled out. Okay. So, but anyway, I know the following is the truth. That J dot N ds. What this means? This means that
The current density.
current density times area means N is this little surface in here.
Okay.
J dot N ds is the current coming out of that little surface.
Right.
This integral integrate over this
Yeah.
means it's the net current flows out.
Yeah. The flux.
The total number of amperes flowing out.
Yeah.
Okay. So this must represent if the current goes in equals the current comes out, this will be 0. Right? Because somewhere this current is coming out is positive, but there's somewhere it goes in is negative. So therefore this is a net current flows out. So this current here, this is representing total net current flows out. This must mean this must mean equal to the total dq dt. Means inside the here is charge. Q is inside here. Is losing. Because if you have a more current flows out, means the charge inside must be decreasing. Must be decreasing. Okay, flows out. So that we have a minus sign here. dq dt is increasing, right? The rate of increasing is dq dt. So minus is decreasing. So this must be true. This equation is called the equation of continuity. Charges cannot be destroyed. Okay. So you have this relation here. Now, if we instead of taking this big sphere here, if we take a small sphere here, all right. So therefore, we will have this side here. Well, if it's a delta S, this will be delta Q. All right. This will be delta S, delta Q. Now, delta S, this is what? Okay, this is, now I'm taking a small one, then divide by delta V. Divide by delta V. Then take the delta V go to 0. What is this equal to? We just did it earlier. What we did here.
Wait.
You take a look at your notes.
No, I know it's there. I just was trying to think what you were where you were leading this, and I got lost in that thought. Sorry, I drifted into why are we doing this and where we're going with it.
Yeah.
Okay.
What I want to, we're doing it is trying to get the displacement current into the picture.
Right.
Okay. Okay. How can we get the displacement picture? Because there's some ambiguities. If we didn't have this term, if we didn't have this term, then we will have ambiguities.
I don't understand what the d by de is. Okay.
ddt.
dt, yeah.
Okay. That's mystery. It took somebody like Maxwell to understand that.
Okay.
Okay, so I'm getting to it. I said, this is the Maxwell's equations.
Right.
Okay, now I'm picking it up over my head and wrote it down. You say, no, wait a minute here. What you had was this. What we did
Yeah.
before. What we did was this.
Right.
Okay, how come you put something like that in here? Right? Why you put that in there? Okay, I'm sorry, I didn't know. I didn't know why, because Maxwell said there ought to be something like that in here. Okay, then the question is why? All right. To answer why, we must go back to something more fundamental.
Okay.
Okay, this something fundamental is the equation of continuity.
Okay.
Equation of continuity means if you have a electron wind blowing, you take a closed surface
A volume.
of a volume with a closed surface enclosing a volume,
Right.
then we know that this integral, okay, this integral is the net number of amperes
Flowing
coming
through.
out of this surface.
What about going in?
Net, just
In
in and out, all canceled out afterwards.
So that's the current.
That's the net current
Flow.
flows out.
Okay, that's
Okay,
QDT.
3 amperes this way, minus 2 amperes that way, 5 amperes that way, and so on. Add all those numbers together.
Okay.
Okay, that number means you have, say, 2 amperes net coming out, which may be 3 going in, 5 coming out.
Okay, great.
Okay.
So,
So, which means net inside here is losing 2 coulombs per second.
okay.
All right. So therefore, dq dt is equal to minus 2.
That's your current.
That's your current.
So,
Okay. This, in other words, this relates the current with charge.
yeah. So,
All right. So this is only starting now.
okay.
All right, now what happens is that I can do this with a big sphere or small sphere, medium sphere. I can do it any sphere. I do it with a very small sphere, delta S.
Okay.
So then that means this is net current coming out of that small delta S, which means this is net losing of the charge in that small surface,
Right.
delta Q. All right?
Right.
Then this is mathematics now, divide both by the delta V, and take limit at delta V go to 0.
Okay.
Okay, so this becomes del dot J. Just by the definition of del dot J, the divergence,
Right. Okay.
right? Okay, so del dot J equal to minus, what's delta Q over delta V?
Change in current and the change in
Don't
volume.
use the word change. Delta Q is the charge inside this little box.
Right. That's the box.
Delta V is the volume of the box. What's the
Charge
ratio
for,
of it?
charge for density. Charge for size for volume.
That's charge density.
Okay.
That's
J.
called charge.
Rho.
That's rho. Okay. So that's rho. So this is d rho dt.
Okay.
What's the big deal about
It's not a big deal. It's just well,
Why you have any questions?
I don't have any questions, but I just don't know where it's going.
Okay. So just you have to be patient, right? Takes Maxwell, somebody like Maxwell and Faraday and all those people before him couldn't find an answer to this. So by that, okay. So now we go back to this del cross H bit. Right? That was what we obtained before.
Right.
Okay. So if I take a del dot on both sides, right?
Yeah.
This ought to equal to minus 0 dt.
Right.
But this will be 0. Okay.
Del squared H. What is that?
Del dot del cross. The divergence of a curl is equal to 0 identically.
All right.
Okay. Let's see why. Okay.
Just use your.
Curl is ax, ay, az, d by dx,
Just do 2 dimensions.
dy. I know d by dz, hx, hy, hz. Okay. Now del dot that is d by dx on the x component. X component is dhz dy minus dhy
DZ.
dz. All right? You're not getting anywhere. But if you do the other component, the y component, is a d by dy plus dhx dz minus dhz dx.
Why is that so?
Not yet. Then finally, d by dz on dhy dx minus dhx dy minus.
Yeah. So.
Now you see it's going to be 0. d square hz dx dy. d square hz dy dx minus.
Okay. Yeah. They all cancel.
They
Okay.
all cancel.
All right.
Okay. So therefore, this is equal to 0. This left-hand side here it's not physics. It is mathematics that says the divergence of a curl is equal to 0. Whatever you have in H in here, whatever this physical quantity of that thing is, may not need to have any physics in it. It is just a mathematical consequence due to this. Okay. So which means now, this equation is something wrong or incomplete. Because from the physics, we say del dot J must be equal to d rho dt minus d rho dt. Here says del dot J equal to 0. This is the inconsistency. So Maxwell then began to think, what to do, don't know what to do. All right. He then thought about it, just using the concept as the current flows into a capacitor. It charges the capacitor, but in the space, the electrical field between the two plates should be counted as part of the current. So therefore, he adds this quantity to it. Okay, let's see what happens then. If I do this, so del dot del cross H, therefore it's equal to 0, right? Which is equal to d by dt on del dot d plus del dot j, right?
Right.
What is del dot d from here?
Current density.
No,
Rho.
rho is what?
Charge density.
It's charge density.
Right.
Okay. So now you see, this is exactly that.
Yes.
Right. So there's the remove that
Ambiguity.
ambiguity. All right. To see now this okay. Now let's take a look at the electrical field due to a point charge. Right.
Okay.
So multiply both by epsilon. Okay, let's take the epsilon. So D. Right. So D, the units of D is what? Coulombs per
Meter squared.
meter squared, right? So coulombs per meter squared, d by dt on that. D by dt on coulombs is what?
Amperes.
Amperes. So it's amperes per meter squared.
Yeah.
Okay, this is also amperes per meter squared. So this quantity here has the dimension, has the significance of a current. So you call it displacement current. Has no meaning. The word displacement is actually a wrong for number. It's a wrong term, but it used for historical reasons, just simply because Maxwell used it. Why he called it, Maxwell called it the displacement, the D vector. E is electric field. D he called it displacement vector. Why he called it displacement vector? Because it's the result of the charge gets displaced under the influence of the electric field.
Okay.
So it is hand waving. Okay. But anyway, history said the great man used that term, we used it. So we call it displacement current. So now we have 3 Maxwell's equations in one afternoon. It's a big rush. You need to go through this. Finally, let me just make this one in here. Okay. Right?
Yeah, I remember that.
Okay. This is Faraday induction law.
Yeah.
This is,
And dp dt vector.
yeah. And we have only one turn in here. So this is equal to delta. This is equal to any loop. Now if this is delta L, E dot dl, equal to minus d by dt and delta phi. Okay. Delta phi is B times delta S.
Where did you get that?
Delta phi, now what do we do?
Oh yeah, P is
Yeah,
P
it's
is the number of magnetic field lines going through the surface S.
B is density.
Right.
Okay, so this times that. So so divide by delta S, this goes out. Take the limit, delta S go to 0. So this becomes the curl of E equal to minus dB dt. dB dt is j omega mu h. B is mu h. B is mu h.
Mm-hmm.
D by dt is j omega, and this minus sign is that minus sign, that minus sign. So del cross E equals minus j omega mu h. So Maxwell's equation is complete. Okay.
Great.
Normally, I would want to spend something like 2-3 weeks on such a subject. So if you're a bit kind of groggy, it's anticipated. It requires you to do more than just getting the exposure of it. The same thing as we did before. In the past several months, we covered a lot of things. From the circuits to resonance, bandwidth, and transmission line. You have to really put in a lot of energy when you're on your own time. Whether it's at work, I said you may count this as work doing it. You should do this as if you are on your own, at your own time. You should try to do that because this is professional. You cannot do it with like you play the piano. You play piano, you have the piano, you fool around with it. You get excited by doing it because you get to play with Lauren Holland. That's your motivation. You never thought about you're going to become a professional. If you want to be a professional pianist, Holland does this 10 hours a day and so on. 20 hours, and whatever the number of hours a day you have to do. You have to spend hours and hours of lectures, have to be screamed at by the teacher, and my hands, that sort of thing, the kind of stories like that. You want to be a professional. And you want to be a professional in this stuff, you have to be that kind of leader. Otherwise, everything is a game. You will never get very anything. I believe that making movies is the same thing. I don't think making movies can be done by amateur. You need a lot of, you need equipment, you need a lot of understanding about a